Okay. Hi, Neil. How are you doing? Welcome, everybody. How's it going? Yeah? All right. So this class should be with Group B. All right? Or I guess, yeah, it should be with Group B. If you are in Group A, please run over to the lab and do that lab. Okay, that's you'll be in EIT or the DSP labs. Okay. Administratively, are there any questions about what we're doing, how this class is set up? No questions? Clear? Okay, so where are you going to be on Thursday? Is that clear? What's that? Huh? Yeah, so most of you will be in DSV, and then some of you are doing the virtual section. Okay. That makes sense? And then the lab 1 is due at 4 o'clock on Thursday, so you should have some time to get that done. You can do it now. I mean, you could. Actually, how many of you already did lab 1? Okay, some of you already did it? All right, so, huh? Okay, you didn't do the post lab yet. Okay, but you've already done lab 1. Great, okay? And then the post lab will be due on Tuesday before class, and that's good for everyone. All right? I mean, that's administratively, that's how we're working. Okay? Great. Well, it's nicer to have the class. It's nice to have the class in a couple of sections, so that we're a little bit smaller, so hopefully we can have some interaction, some discussion, and it will be less likely that we all fall asleep. Okay, so today, what we're going to do is discuss an approach or two to simulating the dynamics of particles. Okay, and these are particles that mostly will be interacting through gravity. Okay, it's just a light. It's not the screen, it's a light. And then we'll, so those two approaches for these types of simulations will be using the Euler Method, which I think many of you, I mean, how many of you are kind of familiar with the Euler Method at this point? Okay, well, you did the lab. So yeah, so you should be familiar with it. Okay? Does it sound familiar? Yeah, a little bit? All right. I think it's one of the numerical processes that they teach in some of the Intro to Computing courses, classes, and in some of your calculus. Okay. So Euler Method, yes, no? I'm just wondering how bored you're going to be if you go through Euler Method. Okay? And then we'll talk about something which I don't think you would have seen, which is the velocity Verlet method. And hopefully we'll give you some insights in terms of how you do the lab and the post-lab assignment, focused on orbital mechanics and geosynchronous orbit. Geosynchronous meaning the satellite around the Earth should be in sync with the Earth's solar. At the same time the next day, it should be in the same spot. Okay, that's what we mean by geosynchronous. Okay. So, here are a couple of particles, and maybe gravity is acting between them. Okay? Very likely. In fact, if it has mass, there is going to be 6+1 under gravity. And they'll be attracted to each other. Now, when we think about a particle, what do you think? Okay, we're thinking about this particle. What are the parameters that might be of importance to you? You're thinking about simulating the motion of a particle. What are the important parameters? Or what are the things that we're going to be tracking? Yes? Mass of the particle. Okay, so right? Okay, so good. That's interesting, right? So we want to know the mass of the particle for our intents and purposes. So this is not like, we're not going to do a problem where we have a rocket that has propulsion and it's losing its mass, okay? Because that's one way you can think of a particle, right? As a whole vehicle can be thought of as a particle. A whole galaxy can be thought of as a particle, in fact, right? But okay, so maybe I didn't phrase the question. Motion. What are the parameters associated with motion? What are the variables associated with motion? So velocity, yeah. What else?
Position.
Yeah, position and acceleration, right? Those are the three, okay? And so we're going to be keeping track of position in a vector. We'll be keeping track of velocity in a vector or an array or a container, okay, we call these. And we can also be considering acceleration. Now, if I have a particle that is falling on Earth, okay, there's no wind pushing it around or anything like that, that particle, for our intents and purposes, is going to have a constant acceleration, and the vector for that falling particle is going to be constant, okay, for the acceleration, right? It's going to be going toward the center of the Earth, and it's going to be falling with an acceleration of 9.8 meters per second squared. Okay, so those are the vectors that we can keep track of. And in addition to thinking about this position, the velocity, and how acceleration affects them, there could be multiple forces acting on that particle, right? So if we want to figure out these parameters where we're going, we can think about superposition. Okay. So the 4 steps that we'll use over and over again are: 1, to establish the physics and discretize the problem appropriately. We need to start the simulation. We need to have appropriate initial conditions, and we want to make sure that we're within the boundaries of our problem, or if we cross a boundary, if we get next to a boundary, that the appropriate effect happens. And next week we'll talk about bouncing balls, and we'll talk about boundary conditions in that sense. What happens when a ball hits the ground? How do you simulate that? And then you're going to run the simulation through a series of steps. Okay. This approach is going to be something that we keep using across multiple domains, whether we're doing a heat problem, whether we're doing a orbital mechanics problem, we're doing a dynamics problem, mechanical problem. Okay, we have to kind of establish the conditions for these different steps, and then think about how to repeat them. So when we think about physics, there are Newton's laws, which you're familiar with at this point. Okay? And we've kind of started to think about the position, the velocity, the acceleration. And in the analog world, there's not really a discrete number of locations. There's not really a discrete amount of time, right, in which we're operating. Okay? And we have lots of people's different clocks running when it comes to time, and that's the beauty of an analog world. When we do simulations, we're breaking up our problems into chunks that a computer can handle. So sometimes, okay, many times, we have to think about discrete components, discrete quantities. that we're going to keep track, and that is what discretization is. So discretization means that we're going to break a problem into segments geometrically or in time. And for particle dynamics, and if we're talking about orbital mechanics, or we're talking about this ball falling, if you're thinking about, okay, position, velocity, acceleration, how are we thinking about the chunks that we have to break the problem into? And how are we going to discretize this? We have some choices, and we just said it's geometry and time. Well, what would you say? What would you say if you're trying to track a particle and its motion? How would you break it up? How would you discretize this problem? Yes, Neil.
Time.
Okay, time. Why do you say time?
Well, the 2-point particles, right? So there's not really much geometric complexity there.
Yes, yes.
Also, motion itself is defined in terms of position.
Yeah. Okay, good, good. All right, so we have change in position over time. That would be like a velocity with some direction, right? And yes, at a bare minimum, we've got a discretized time. Okay? So we're going to say, oh, we're running for 1 second the entire simulation, and maybe we're running, you know, our different time chunks at a tenth of a second. You've got to have a, you know, typically we start at 0. We say, hey, our initial time is going to be 0, and our final time is going to be something, and then we break it up. Space, we can kind of think of as being continuous, right? So that particle could be here, 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 wherever it is, but I'm not going to draw a grid in this problem and say your particle can only be at the intersection of this x and y axis, or your particle can only be here at this intersection of the x and the y's. Okay? It's going to be fluid in how it moves around. Okay? Now, when we do mechanical problems, you all remember from mechanics and materials, at least if I was teaching it, right, in the last couple years, we've been doing some finite element analysis. So in finite element analysis, the name of that simulation kind of leads to this idea of I have a finite number of elements, and that's what's going to go into my mechanical structure. So in addition to discretizing time, and sometimes time is a little funny in some mechanical simulations because it's static, right? We're actually thinking in terms of, you know, I apply a force here. I'm not thinking about what happens in the transition from location, from the force going from 0 to 1 Newton, although that's actually kind of how simulations work. But we definitely are simulating discretized space. Right? So here we're breaking the time into segments, and we are saying that the geometry is going to be continuous. And what are we going to be doing? We're going to keep track of the kinematics. Okay? And kinematics are the positions and the velocities. Okay? That's describing the motion. Now, there's a difference between kinematics and kinetics. Anyone know the difference between those two? You've heard both of these, yes.
Kinetics include forces.
Yes, exactly, right? So this, you could argue that we're not really just doing kinematics here. You know, once we add, you know, we need kinetics as well, right? Has the forces, right? The inertias, right? Plus the motion, right? Which is just kinematics. Kinematics is kind of like, I've got a pendulum on at a joint, right? And it can only move, I'm stiff, right? But it can only move about that joint, right? The kinematics are dictating. So in like mechanisms, if you take a class of mechanisms, you're looking at multi-link joints, 4 links, whatever, you're thinking about kinematics a lot of the time, right? The motion, you're trying to control that. In terms of just what is the geometry that it traces out. When we talk about kinetics, yes, we're introducing the idea that this is a dynamic system, and there are going to be forces. Newton's laws are going to be taking an effect. So here, what you see, and it's written in multiple subscript notations, okay? In a discrete form, that could be not just a t, but those could be natural numbers or whole numbers, right? So if you're in Python, the computer language, not the animal, right? If you're using Python, those matrices, those arrays are usually 0 indexed. But if you're in MATLAB, the arrays and the matrices, the vectors, those are 1 indexed. All right. So natural numbers, right, would be 1 index, whole numbers, and you're not going to go negative, obviously. You could. I mean, you can backstep, I guess, in time, but we're thinking about kind of, again, discrete motions of time. So this could be like t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, right? And then we're piecing it together. Now, how do you think, before we kind of talk about things further, how would you pick a time step? So now we're talking about, okay, I'm iterating through time. So what are the things that go through your mind when you think, oh, well, if I've got to discretize something, how do I chop it up into time? What do you all think? How am I going to, I have some simulation, I have some particles, I want it to go, what are you thinking about in time? Okay. What's your name?
Rohan.
Rohan? Yeah, Rohan, go ahead.
Like you can uniformly calculate something that time.
Okay, so okay, all right. So let's be even more engineering-like, all right? How do you pick your steps? Yeah.
If you have an object that's changing very quickly, so its acceleration is very low, you want smaller time steps because time step a lot of change can happen.
That's right? So so one idea is that your time steps need to be some fraction of whatever the overall time that you expect your simulation to run, right? So, if I'm interested in simulating the travel of the moon around the Earth, probably not going to use units of years. Okay, initially, like, oh, I'll just do 1 year next. It will shoot off. All right, I won't be able to track. I won't be able to capture the dynamic behavior that I expect. Okay, so then you want to make it small. What's the problem with making it too small?
It takes forever.
Well, what takes forever?
Like running the simulation.
Okay, right? Yeah, okay, is that what you're going to say? Right. So, yeah, obviously you can't pick an infinite number of time steps, right? Because you'll never get anywhere, right? And so computationally you have to kind of make a trade-off. Okay? As we're talking, we'll talk a little bit in lab 1, and the post-lab exercise will get into more details of what this trade-off is as it relates to something called convergence. Okay? So we'll get back to that though, but let's talk about how we go about discretizing. So we will discretize again time, all right? Continuous position, all right? We already said this. And now let's use an example. So the example we're going to use is of a particle in free fall under gravity. So we were already thinking about this a little bit, right? And if we have the particle, we can draw it like this, and we can say z, that position. Okay, so this is a 1D problem, right? So probably not a good idea for your final project, like we discussed last time we met, to do a 1D particle dynamics problem. Okay, and if mg, that's the force, right? Gravity's acting down. What do we expect? We expect z to go positive or z to go negative, right? We expect z to increase, right? At least the position of the particle to increase with z. Okay, and we'll say that it starts at 0. Okay, now first let's think a little bit about the analytical solution. So analytical, right, means we have a closed form equation that we can use. It's not really simulating. Okay? I mean, sometimes you use closed form simulations, and you do kind of simulate, like, okay, this is where it would be. But in this case, this is not the type of simulation. This is not a particle dynamics simulation. This is the exact solution. Okay? And then in simulations, we'll also talk about Euler Method, and there can be other forms of the Euler Method, and then we'll talk about Verlet in a little bit too. Okay, but let's go ahead and let's do the derivation of the analytical solution. Initially, it's at 0. The velocity also initially is 0, right? So if you're thinking, oh, this is like an ODE problem, I've got my ordinary differential equation problem, I've got my initial conditions where velocity is 0 and the position, the particle is at rest. The acceleration, we can say, is just going to be g, right? It doesn't really matter what the mass is. Okay, we're assuming that it's much, much, much smaller than that of the Earth, and that we're going toward the center of the Earth. So for the 1D problem, okay, we can write position as z. We can write acceleration as z double dot, which is equal to g. And if we did, and we can write that the velocity is going to be z dot. That will be, well, you tell me. What is the velocity? What is the equation exactly? Here I've got g. Yeah, right. So I just integrate, right? I integrate the acceleration, so I get it's g times t. Okay? And then if I want to know position, what do? I integrate again. And these are indefinite integrals, but since we said that the initial position and the initial velocity is 0, those constants are 0. Okay? This is the exact solution. Not particularly interesting from a simulation perspective, okay? But if I know where I start, okay, or I know how far I've traveled, maybe better said in this case, because we're starting at 0, right? If I know the distance I've traveled, I can figure out how long it takes, right? And vice versa, if I know how much time has transpired since I released the particle, I know how far I've gone. And if I know how much time has transpired since I released the particle, I also know what my speed is, or my velocity, right? This is our first example of ground truth. So when you're doing simulations, if you can, you want to try to compare to ground truth. You want to try to compare to baby steps, right? Some of you heard me talk about baby steps when we did finite element analysis, right? So if we were, simulating the extension of a bar, mechanical bar, right? We had a force, we had a cross-sectional area, right? We could use F equals K delta, or we could do that, we could use Pli, we could say delta is equal to PL over EA, or FL over EA, Pli, whatever you want to use, right? But you've got these analytical solutions that you can say are pretty close to ground truth. And then you put it into the simulation, you're like, yeah, that's what I get. That's important, right? Because you want to do more complicated things. But if you set up your simulation and it doesn't do the simple thing, there's no way it's going to give you an answer to a more complicated structure. So it's often wise to start with kind of baby steps and start with ground truth. So that's what we're going to do here. So we've kind of established what the physics are. We have F equals ma. Right? We've got the second law going for us in motion. Fun. All right, never had fun. All right. Then we're going to initialize the simulation. So we're going to start the start the problem, which it can be a little bit tricky. Okay, to track the initial conditions with vectors and matrices, and like some people don't even track it. So like sometimes it's just like, oh, I just put in my container, which is a vector, I just put the first time step. So just make sure you know this, and this is confusing. See, I get confused by these simple things. Right? So you may not get confused by these simple things. But when you make your container, when you make your vectors at your tracking position, you want to decide, is the first element in my container where I'm tracking everything, is that going to be the initial condition or not? For our intents and purposes, it's usually a wise idea to say that's the initial position. But then when you come full circle, then are you at like n plus 1, like the number of total steps that you're using, or at you at n? That also can be tricky if it's something that's cyclical, like geosynchronous orbit. And then, okay, so in this case, the acceleration, it's constant, right? In orbital mechanics, is the acceleration always constant though? No, what's going on? Why is it not always constant in orbital mechanics? What's happening to acceleration in the case of satellites going around the Earth? Yes?
The direction changes.
Okay, direction changes, right? Why and your name is? Shrima. Okay, so direction changes, yes. What else changes? Yeah, so you could say, if it's like way out, right? If you had a really large orbit, right, and the distance changes a lot, right? That could also affect the magnitude, right? I agree that if you have a circular orbit, right, then yes, the direction is just changing. But let's say it's like elliptical and the thing is shot way out there, right? Then we know that gravity is going to be decreasing as we get further away, and as we're closer, the gravity is going to increase. And we also know, maybe we know that sometimes, we use these effects, right, to kind of slingshot something back out into space, right? So, good. And we'll talk about the gravitational potential in a few minutes. That kind of explains how we look at this changing acceleration in orbital mechanics. Okay, so boundary conditions. For this, don't worry about it. Okay? Even in this simulation, if you were to mess it up, right? And we'll talk about interaction between particles and bouncing and molecular interactions and blah 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 a little bit. But there are points. If you could design your particle simulation so that the satellite is going right through the Earth, right? If you're not careful, then we don't care about these boundaries. That's the case. And then the real trick is to figure out, okay, how do you iterate through these different steps. Okay, so let's take a moment to kind of digest and stretch, if you want, your legs, whatever, you're probably like, this is now getting to the boring section, my attention span is going down. what are the types of forces that we might apply to a particle? Gravity is one, all right? So don't say gravity, right? So we know that we have gravity. What else? Yes, and your name is?
Brian.
Brian? Okay. Brian. Magnetism. Okay, so magnetism. So you could have magnetic forces, right? These are body forces. Okay, then someone else, yes? Okay, impact. So you could have contact. For our intents and purposes today, we're avoiding it today. Okay. We'll return though. Okay, what else? Yes?
Surface force?
Okay, so what would be a surface force?
Like
Okay, so see, this is interesting. We're talking about particles. So you are right, surface tension, right? You could even think of a particle experiencing friction, okay, on a surface, right? Surface tension is more like a continuous fluid phenomenon, right? But yes, I get what you're saying. So we could say there could be friction. Okay, what else? Yes? Okay, so rotation as a force. What do you mean by that? Okay, so let's say you could experience some type of centripetal acceleration or centrifugal force, right? So we're thinking about body forces on particles right now. Okay? So yes, our particles, we're actually not considering the angular momentum of the particles, like how they're rotating about their own axes. Okay? We're just thinking about it as a point in space. We've eliminated that degree of freedom, okay, or degree of complication. So yeah, we could say centrifugal. Okay, what else? Yes?
electric?
Yeah, so we have electrostatic. Okay. So you could have a positive and a minus, right? Charge is Q. We have Coulomb attraction, Coulomb repulsion, right? So Coulombic interaction. Yeah, these are pretty good. People often say, okay, and then anything else people want to contribute here? These are kind of the forces that can be acting on particles. And then if you get into the particle physics, people will talk about the weak force, which leads to the degradation of the particles themselves, and the strong forces that leads to or is why the particles stay all compacted to each other. We're not going to be doing particle physics in that sense here. But what we're talking about is, of course, relevant. But the strong and the weak, we're going to leave alone. All right. We can treat these multiple forces, acting on an object through superposition, right? That's nice. And then, what are physical systems that we can represent with these particles? What physical systems might you think about?
Solar systems.
Okay, so solar systems, yeah. And what's your name? Changgu, okay. We'll put in galaxies as well. All right. What else? Yes.
Quantum systems.
Sure. Why not? But it's beyond me. Okay. Yes. Okay. What do you mean by that? Yeah. I mean, we can think, yes, we can think about, we'll think about potentials, right? You know, gravitational potentials, we'll think about kinetic and kinetic energy as well. So yeah, you can think about, for example, molecules, right? Gas molecules. So we'll just say gas, right? So you can think about these interactions from a particle perspective. Okay, so when it comes to things like simulating fluid dynamics, yes, you can do it from a particle perspective. Practically, we do not. Okay, we'll cover a couple of approaches. You can use what are called the finite element analysis, finite elements, and you can also use finite volumes. These are kind of two of the processes that we'll talk about when we get to covering fluids. Gases, though, you could argue a little bit easier to think about in terms of particles. But of course, you can think about particles and fluids as well. Right? And often when you're using these simulation packages, you do, how do you say it? You seed your simulation with particles, okay, just to kind of see what the motion of the fluid actually is. So you don't give these particles any inertia. They're just tracking, you know, they go along streamlines essentially. So imagine like Bernoulli's Bernoulli flow or something about sphere, foil, whatever it might be. So you can have particles there. Okay, I like that. So you can think of gases. You know, you could think of, we'll say fluids with kind of an asterisk. And you said thermodynamics, right? So as you heat up a system, the kinetic energy goes up, right? And you have more and more activity in that system, more and more interactions. Good. Any other thoughts? Great. Okay, so here's the Euler method. You can read through it. But let's just talk about what it's really doing. So we said you start off at a given location, okay, and you have, in the case of a falling particle, which is what we're simulating, let's just say that I'm that falling particle and I'm following that direction. The Euler method essentially is the process of numerical integration using my current information to predict what's going to happen at my next time step. Okay? So, what do I know? I know that I have gravity acting on me. I know that my acceleration is going to be 9.8 meters per second squared. We're saying fictitiously in that direction. And so, I want to predict what my velocity is going to be in the next time step in the future. Okay? So you kind of already did it, right? You said, oh, well, GT, right? You said GT. That's a closed form solution for velocity, right? But I can take my initial zero velocity, and I can take my time step, maybe it's 0.1 second, and I can say, okay, at my next time step, I haven't really even talked about where it is yet, okay? But I know that my velocity is going to be gt, or g times the time step. Okay? So what we do here, okay, remember all this, is we create a column vector, okay, on the left that is going to have our velocity and our position. So z dot I plus 1 is the velocity in the next time step. Z sub I plus 1, okay, or n plus 1. However, it's a little confusing, whether you use a subscript as n or use it as I. So let's just say that in the next time step, I've got a velocity and I've got a predicted position. Now, on the right, what you have are some guiding equations that discuss what's happening in the current time step. Plus an expression that then gets you from the current time step, so this would be the current time step, plus some expression that helps you understand what is in the next time step, right? So, this is probably obvious, but this row corresponds to this row corresponds to this row. Okay? So this equation is predicting what's going to happen in this row in the next time step. This equation is predicting what's going to happen to the next position in the next time step, the position in the next time step. Okay? And here, what we're saying is these h's are the time step, and you see that this parameter is the derivative of this parameter, and this parameter is the derivative of this parameter, right? Because I'm taking, right, what's the derivative, right? It's like whatever that quantity is, with respect to time, right? I've got that quantity essentially divided by a dt. Okay, over simplification, right? But that's what we're talking about with these time derivatives. So what we end up doing is we end up working through all these very simple equations like an accountant. Okay? And the good thing about a computer is it's a great accountant if you tell it what to do correctly, right? So here is, we're not going to go to more derivatives. Okay, we're just going to keep track of the position and the velocity. So we have just these two rows here, and the top row is going to be talking about position in terms of, or the position in the next time step based on the position in the current time step, and is a delta t times z dot. So if my initial velocity is 0, I was talking about the next time step, all right? And I was kind of saying, hey, it's here, but in reality, okay, if the initial velocity is 0, and there's a time step, the next position, right, is going to be 0, because my initial velocity, my velocity at this first time step is 0. Which means that if I multiply 0 times delta t, that's still 0. Okay? And if I think about, though, the velocity in the next time step, I might be at this location, but at least now I know that I have a velocity that's equal to gt. Okay? So that now when I move in position when I move now in position, that will be like the second time step, right? Because now I will have a new velocity, all right? And I can multiply by my time step to get me a new position over here. Does that make sense? So we'll go through this. It's often not a bad idea to kind of make a little grid like you see here. Okay, so we have I, which is our step, and we have zi, z dot I, z double dot I. Okay, we have our next time step, we have our time step, and we have our position in the next time step, and our velocity in the next time step, and we can compare this to the truth. Spoiler alert. They're not going to agree, ground truth and our simulation. Okay? The question is just how bad will that disagreement be? Okay? So let's work through it. Let's say that our initial conditions dictate that we have, like we were saying a second ago, 0 position, 0 velocity, but g. And g is going to be the same throughout this experiment. Let's say that the time step is something simple. It's 1 second. Okay. Should probably put in units. I'd be annoyed if someone didn't put the units in. But anyway, those are the units, right? And these are meters per second squared. This is meters per second, and this is meters. Okay. All right. So, what do you think we should do? Well, let's look at filling out these blocks. Z of I plus 1, like we said, is just going to be 0. Right? It's this quantity, and z dot I was 0, and delta t was 1 second, so zi plus 1, sorry, zi is 0, so zi plus 1 is just 0. And now, what do we do here for z dot I plus 1? Well, it's got a delta t, we've got an acceleration, and we've got a z dot 1. Pretty straightforward, right? We'll say that this is also 0. Okay, that's our initial position. So that's pretty good. We agree with ground truth when we haven't done it. What do we do next? What would you do? If you're approaching this problem, what would you do to get to our next time step? Ideas? What do we do next? Okay, yes, go ahead. I can't remember your name. What's your name? Vermont. Okay, so what's up? Okay, right. So what are we going to do? We're going to say, let's take the information in the I plus 1, right, here, and just move it over here, right? And g is the same. So we move 0 and g right here. We have g, and we're in our first time step, and we have 1 as our delta t. And then we can calculate out zi plus 1 and z dot I plus 1. Just like this. So z of I plus 1 was going to be taking the z dot I, which is g, times 1, plus the 0 that we had there to get g. And here we had our g, we had our 1, and we had g. That becomes 2g. What is this? This is just g over 2. Okay? So we already realize we're off. Okay, we're off. So we can keep doing this. I won't bore you. Well, maybe I could bore you. I've bored other people doing this. But we'll go through this grid as you see here. Observations. What are your observations here? Anything interesting? What have you observed? You're smiling, so you've observed something. Yeah, I don't know. Maybe it sounds like it looked like there was a light bulb there.
Well, the I plus 1 looks like it's decreasing or increasing at the smallest rate, and then gt squared over 2 looks like it's catching up to the first one, the I plus 1, but not really.
Yeah. Right. So like you can see that there's kind of, okay, we went from being off by a factor of 4 in step 1. Now we're a factor of like 50% off in step 2. Now we're a factor of like 1/8 in step 3, right? So it's like we're kind of moving, we're progressing along. We're seeing some trends. And there's some error there. Okay? This is probably too obvious, but I'll ask. How can you decrease this error? Sure, since it's almost rhetorical and you were talking, what would you do? Yeah, exactly, right? You say, oh, hey, if I do like 0.1 second, right, then when I start looking at it, like at 1 second, do I expect the error to be larger or smaller? Yeah, it's going to be smaller, okay? Because the Euler method converges, okay, for these types of problems. So you had to pick the method. You had to have a method that converges for the physics that you're using, or you hope will converge. Okay? That means that you're getting to a more accurate solution. That's one meaning of convergence. Now, this process is what is called also called as the forward Euler method. We're marching forward in time, and there is a distinction between these different types of numerical methods. Some are explicit and some are implicit. All right, and this is not like they use some dirty words, explicit. Okay, this means that it computes the next step based on information in the previous step. Only information in the previous step. And you're like, okay, that seems to make sense. That would be the logical thing to do, right? Implicit calculations are when you have equations, all right, like this. Like say y, let's just use this one. Y sub I plus 1, right, is a function of y of I plus some type of function of y of I plus 1. Like what? So implicit means that they have developed equations to predict what's going to be happening in the future. Okay? And these are often complicated expressions, and they sometimes don't converge. So they're very sensitive. For now, we're just focusing on explicit calculations. Now, here's some code. If you open up your MATLAB and you have some fun, let's see if I can do this. All right, yeah, so I think this is the right script. Yeah, so here is the first introduction of a code. Okay. We're going to do 3 iterations. We're going to have gravity. We're going to have a time step equal to 1. And we are going to have our initial position at 0. We're going to have z dot equal to 0. And we're going to have z dot dot equal to g. And then we're going to create some containers. The containers, we can, in this case, I'm going to say that my first element in the container is my initial condition. Okay, does that make sense? So now I've defined a vector, or a matrix, or an array, whatever you want to call it, that has one element in it. And MATLAB will tell you, you know what, you really don't need to use brackets if you're just setting the variable to one element. Okay, that's fine. MATLAB will also tell you, this is a really bad way to do it in terms of keeping track of vectors. So what they often want you to do is define the length of the, like even if you're using like a zeros or a ones command, okay, and if you're not familiar with these, you will be, all right? Zeros is a command that just populates either the array or the vector with zeros in it. It's very creative in its naming, right? So zeros, comma 5 would give you 5 elements of 0. I don't even remember if it's up or down. I don't know if it's a column or row vector. But we can find out. Oh, okay, it's a matrix. Sorry. I should have remembered that. this would be a column vector, and this would be, sorry, a row vector. Okay. So anyway, if you want to save space, it's often a good idea to define the length. So like if you know you're going to have a million iterations, you could go ahead and make your container have a million zeros in it to start. And then as it runs through, it just replaces those zeros. So that MATLAB doesn't have to continually augment the size of the array every single time. Okay. We have our time steps and we have our errors. This is what the Euler method looks like in a for loop. Okay. And if you looked at the kind of the MATLAB review stuff by Marco, like he talks, it does like this little thing like for loops really aren't the fastest. Right? There are often other ways to do things that are faster. Like have MATLAB use its compiled code underneath to manipulate matrices. It will go much faster. But we're going to be for our intents and purposes, we're going to be using a lot of for loops, okay, in this class, just to keep track. So what do we have? We have that first row, all right, where we said the next position, all right, I plus 1 is going to be equal to the current position plus the time step times the velocity. The velocity at the next time step is equal to the velocity at the current time step plus the time step times the acceleration. And then the next time step, right, we're going to go, is just equal to the current time step plus the time step. And then we can calculate the errors. The errors, this is ground truth, right? That's the gt squared over 2, and this is what we've just calculated. Does that make sense? Any questions? All right, this should be, I'm not expecting you to necessarily be able to code it the first day, but I expect you to be able to understand it the first day. Okay? Any questions on this? Okay, if you have questions, please see us. Okay? And then we can come out with an overall matrix. What is this overall matrix? This is essentially just what you have here. Okay? We're saying I can create a matrix that has a bunch of columns in it, and we're going to go 3 iterations. And since it's MATLAB, it's going to be 1 indexed, right? But if it were Python, which is kind of like, you know, I started at 0 when I did it here. Okay? And so if you run the code, it's busy. It shouldn't take that long, but that's the matrix. Okay? That's you can see. The first column is what time step we're at. Second column, and the apostrophe is just the transpose. Okay? Right? So it's computing. It's making these rows. These are like if I just plug in ZS, right? It's a row vector, but then I have the ZS apostrophe, and it's a column. So then I can put all these columns together into one matrix. That's all we've done. Any questions? All right. Now, the computer can calculate this very quickly and tell us what the error is numerically. What happens if we decrease the time step by a factor of 10? So here, right, we had quite a lot of error by the time we went 3 seconds in. Okay, 3g over 2. But if we have 10 times as many time steps, that means that we divide the time step by a factor of 10. So now, what you see, for example, is I have to run 30. So this is not, right? This is obviously not every iteration now, right? I'm showing, what am I showing? I'm showing 1, 2, 3, 4, 5 iterations, and these are the last ones. Okay? And this also highlights this time final is 3 seconds, but my number of iterations is not 30, it's 31. Right? This is that classic problem. How many posts do I need when I put up my fence? If my fence is 10, if I need 10 feet, right, of length, and each one of my slats or whatever is 1 foot, yes, I need 10 slats, but I need 11 posts, right? So just again, the counting, keeping track of these things can be a little bit, it's not that difficult. It's just you want to keep it in mind. All right? So this is the equivalent. This is 3 seconds in. And now look, this last column is the error. Okay? There's still some error. Okay? 1.47 meters. Okay? But 1.47 meters is better than 14.7 meters. And this has an interesting property, right? We increase the number of steps by a factor of 10, and the error decreased by a factor of 10. Okay? So we can start to plot how the error at the final time compares to the number of iterations we run. So the number of iterations is the number of steps I run, okay? And it's going to be related to the inverse, right? The multiplicative inverse, if you will, right? 1 over the time step, size, right? Does that make sense? Okay. So another way to chart this out is in terms of percent. So the percent error could be something like, okay, what is the difference of the simulation at a given time step minus ground truth divided by ground truth times 100, right? That would be the percent error. Okay, and that's in the code as well. So we can see here that once we go up by a factor of 10, right? So we had 10 iterations, and we're at 10% error. We have 100 iterations, we're at 1% error, and we're at 10 to the third, and we have 0.1%. This is a log-log plot. Log-log plots, right? The joke with log-log plots is you can make anything look like a straight line on a log-log plot. But it's not true. Okay? Not for this class at least. But often if you have data in an experiment and you're not sure how to describe the relationship, just try putting on a log-log plot and hope that it straightens things out. So here what you see is that and when you've done, hopefully some of you, when you've done some system dynamics and you've made Bode plots or controls or whatever you've done, you've been able to see, hey, remember that slope? That's a -1 slope on a log-log plot, right? But that's a 1 over x, right? A +1, right? If it's a +1 slope on a log-log plot, that's going to be factor of x, like x to the 1 power, right? +2 slope would be x squared, right? -2 would be 1 over x squared, right? That's how these log-log plots work. Because if you take the log of x squared, right, you can take the 2 out, right? You can do 2 times log x. All right, so this has an error that decreases with n to the -1, or 1 over n. Okay? And I just want to point out here that I'm gonna jump to something. Okay. That when you when you're doing these assignments, okay, you're going to get into a situation where you have a choice of plotting the time step on the x-axis or the number of steps on the x-axis. And then you're going to have the error on the y-axis. You can see that these are mirror images of each other, right? Often, the finite element software, okay, is going to, or when you use the simulation software, is going to be trying to plot the error against time or iterations. Okay? And that error you want to go down as you put in more effort, right? As you decrease the time step or you increase the number of iterations you're doing, you want the error to go down. So often what you'll see is that these simulations, when they run, they do something like this. Okay, they'll be like, and it just like starts making lines that go down. Has anyone done this before, like in console or ANSYS or something? It's like, boom, that was a good one, that was a good one, that was a good one. It just keeps going down, 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 right? It's satisfying. It's very satisfying because you got your simulation running and it's starting to, quote, converge. We're going to talk about convergence in a second. But another way to do it is to say, I have a very large time step and I'm going to go backwards. Okay? But usually the plots, we're more used to plots going from left to right. So either it will be 1 over time step, or it will be like number of steps. Does that make sense? They're equivalent, it's just how you describe things. Now, let's talk for a minute about convergence, because this is important. This will be something that you have to demonstrate in this lab and in many of the labs in your final project. And I think I haven't always given well, let's just say I think there's been some confusion about what convergence is. There are essentially 2 ways to do it. Okay? One is you compare simulations or simulated solutions to ground truth. Okay? And when the error decreases satisfactorily, we say the simulation is converging. So in the context of the problem we just described with the ball falling, right? We said that position as a function of time is going to be gt squared over 2. We can take our Euler method and we can decrease the time step, or increase the number of iterations, do the same thing, until the difference between the ground truth and the simulation is, let's say, within 1%, 0.1%. Whatever you say, whatever you specify, right? 0.1%, 99.9% accuracy. That's one way to describe convergence. That's a nice way to describe convergence. We're going to describe convergence that way for the Orbital Mechanics lab and the post lab. What is your ground truth with a geosynchronous satellite? Your ground truth for the initial conditions that we've given you is that in 24 hours, you will be in exactly the same location. There's no drag, right? Nothing, and we've got the right initial velocity, the right position for you to start at, so that you will end up at the same exact spot. So what do? You run for multiple days, and you look at what your simulation, where your simulation says you are after day 1, after day 2, after 2 months, after 4 months. Okay, make sure that you know which one we're asking for. One says 2 months, one says 4 months. You guys are in group B, so you have longer time. So you're going to run it for like 120 days. And that, you want to see that your satellite is exactly where it started 120 days later. Does that make sense? That's your ground truth. There's another way, though. And this is what you do when you don't have ground truth. What do you do? Yes. Exactly, right? What you say, you could be wrong. You could be completely off. Okay? You could be completely off. You hope you're not. That's why you do the baby step first, to try to compare to the ground truth. Okay? But what's your name again? Huh? Anthony. Okay, so what Anthony has said is very profound. You keep reducing the size of your discretization until the parameter or the output of interest changes very little. Okay? So in the case here, we're not doing that. But let's say, oh, I ran 100 iterations. And I'm now like 1.5 meters down. When I run 1,000 iterations, I'm 1.501 meters down. Okay? I don't know if my simulation is accurate, but I know that it's not changing as I increase the number of time steps that I use, as I decrease the size of the time step. That's the other way we show convergence. And this is profound. This not only applies to time steps, it also applies to the discretization of space. So when you're doing finite element, when you're doing the other processes that we're talking about here, as you refine the mesh, as they say, you add more and more elements, finite elements, right? As you increase the number of elements, as you increase the number of nodes, you hope that when you look at a given location, whatever parameter of interest, if it's temperature, if it's velocity, whatever it is, you hope that those values are getting closer and closer together as you refine your discretization in time and space. That's it. That's what convergence means. Okay? And so that's what we're going to be talking about over and over again. Now, Euler method is one way to do things. All right? The other way that we're going to use, and why, so you've asked your question, right, maybe rhetorical. Why would I use a different method? Euler works, right, for our problems. So why would I try a different method? Yeah, go ahead.
Like Euler's imperfect.
Okay, so Euler's imperfect. Let's describe it. Okay, so it gives us some error, right? What are we saying here in terms of imperfect? Do you want to give it to someone else, or like?
I was gonna say like and the steps are always constant. So
Yeah.
that always makes the situation perfect.
Okay. All right. Yeah. So, I mean, and there are strategies where you like change the time steps, right? Like if you're entering a regime where like things are speeding up, maybe you have to decrease the time steps as this interesting dynamic behavior changes. Generally speaking, though, this imperfectness that you're talking about, we can think of it as there could be a faster algorithm, right? We live in a world of algorithms now, okay? And we just saw what happened yesterday to the stock market, right? I think it bounced back today. But a bunch of companies got very spooked when someone said, hey, guess what? We can do all this, large language modeling and everything without your expensive chips. Because what? The algorithm was a little bit different. We're not doing that right here. We're not, we're not using language models or anything of that nature. But the point is that if you have an algorithm for your situation that can get you results with less work, you might entertain the idea. And the velocity Verlet integration algorithm is such an example when it comes to orbital mechanics. Now, sometimes you try an algorithm and you're like, that did not help me. That just made things worse, right? So this is an example of one that can help. And it uses what, you're like, what's the difference between a half step and a whole step? Well, I don't know, musically, there's a difference. You go from the white to black or whatever, on the piano or whatever. Anyway, bad joke. Okay. But the Verlet velocity integration method, or the velocity Verlet integration method, essentially has these 4 steps. One, it says, I'm going to predict what the velocity at a half step is, okay, based on acceleration and using half of the acceleration. I'm going to use then the velocity at this half step to update the position, okay? And then I've got to figure out acceleration, okay? And this I have to figure out using a gravitational potential, okay? And then finally I will calculate the velocity at the next time step. Okay, so it's a different process. When you do the lab, step by step, you type it in, all right? And I'm not asking you to prove this algorithm, but I am asking you to compare it against the Euler method. That's the post-lab experiment. Compare it numerically, right? So you'll be able to see, oh, which one requires few iterations to get to an answer that has less error relative to the ground truth. That's what we're going to be doing for the post-lab experiment, okay? Just real quick, how do you derive acceleration from a potential? We look to our experience in math. Gradients, right? So gravity is the minus the gradient, is the negative gradient of a gravitational potential, okay? Electromagnetism has analogies, all right? The gradient of the potential, or the minus gradient of the potential, gives you the electric field. In fluid mechanics, you can think of a velocity potential, okay, that if you take the gradient of it, will give you velocity, right? So here, you can think of a potential energy function, and as you get closer, okay, as the distance, the r gets smaller, it's in the denominator, right? That means that you're going to have these crazy slopes develop as the distance becomes small, okay? If you have a large distance, the gradient is going to give you something that's, the derivative is going to give you something that's closer to 0, less steep, okay? So essentially what happens is we define a gravitational potential like here, and we can take the negative of the gradient of this potential, here, this is the potential, this is the negative gradient, this is the resulting force, and we divide by mass, and that can give you the acceleration, okay? So just dividing by the appropriate mass, and then you get the acceleration. And that is what we use in this step right here, step 3 of Verlet. Okay? That's it in a nutshell. All right, so we're going to use this technique to be able to simulate geosynchronous orbit of the satellite. All right, so hopefully what we learned today, the key thing I want you to take away is your attendance. No, that's not really it. But the key thing I want you to take away is convergence. Because convergence is what you're going to deal with for the rest of the course. Where is this thing? All right. So, no. There it is. Okay, there you go. Please go ahead and take the attendance shot. I will get out of here. And have fun in the lab on Thursday, okay? If you have questions about MATLAB, let's try to come to office hours. Let's answer them now, because we're going to use MATLAB throughout the course. Thank you.
Professor.